as we get to that. Um, cool. And like I'm home. I hope my Wi-Fi will work fine. I've got headphones, so if I need to try to do something on my phone as well, hopefully we can make it work. But let me know if I'm cutting out. I'll try to watch the chat as best I can. Or just listen. So my plan for today is to focus on talking about galaxy color magnitude diagrams. So typically when we think of CMDs, we're thinking of HR diagrams for stars, but you can also look at a color magnitude diagram for a group of galaxies, and that can teach you a lot about what's going on there. So we're going to start just kind of with a little bit of review of what a color magnitude diagram is, what I mean when I talk about those words, and then we'll get to do a little discussion and work through building our own color magnitude diagrams. So that's kind of my overall plan. Oh, and then I think I said this in the email, but hopefully we'll have some time at the end to talk a little bit about imposter syndrome and growth mindset as a nod to what is going on today. So that's my plan. Let's go for it. Okay. So just as a quick reminder, magnitudes are like the worst unit in astronomy. Everyone hates them, but we still use them. They're based off of kind of how human eyes react to light. So it's not linear, it's not quite logarithmic though either. It's like every step in magnitude is 2.51 steps brighter. So it's funky, and there's also the issue that magnitudes are backwards, or Andrea says backwards, right? So larger magnitudes are fainter, which is fun. And I've got like our little, probably this way, I don't know, the magnitude equation. So going from intensity or flux to a magnitude requires this ratio as shown in that equation. So as we're just getting started, and I didn't actually write down the number, which was a mistake, but if we wanted to talk about actual brightnesses, how much brighter would the 16th magnitude galaxy in this image be than the 19th magnitude galaxy? If people want to, when you figure it out, if you want to throw it in the chat. Should have maybe made a poll. I should probably figure it out too. So when you have an answer, you can put it in the chat to just me, or shout it out, or seen a couple. Levi came back. Oh, don't look at Levi. Three answers so far. So far, everyone agrees. See if we can get two more at least. Okay, so the answers I'm getting from folks, there we go, there's one more, are Around some people are saying around 16 times brighter, 15.8, 15 between, so it's like 15.8-ish. Yeah, I got 15.84. There might have been some rounding there, but somewhere around that. So we can use this equation where we have a magnitude difference of 3. So that corresponds to a brightness difference of about 15, which is 2.5 times 2.5 times 2.5. Or you can just solve this equation, whichever works for you. But just trying to remember that magnitudes are funky. When we talk about magnitudes, there's sometimes you have to flip your brain a little bit to get things going the right way. And you have to remember that they are bigger magnitudes are fainter, which is always the fun thing to keep in mind. So then my next question, since color is kind of a common word, is just to like take a pause for a second to think about what we mean when we measure colors in astronomy. So what, just throw it out, anyone can unmute themselves and just yell out, like what do we mean when we measure color? Why would we want to measure color?
Wavelength.
Yeah. So color corresponds to wavelength. A lot of times when we talk about color in astronomy, the way we measure a color is by taking the difference between two wavelengths. So a lot of times you'll hear B minus V color, where you're taking the difference between the B band magnitude and the V band magnitude, which I'll talk about bands in a second. That's a good transition. But just before I do that, this is kind of showing how especially when we're looking at galaxies, looking at different colors, different wavelengths is going to really change what you're looking at. So this is, I don't actually know which galaxy this is. I should have looked that up. But looking kind of from UV through optical over here, and then into infrared longer wavelengths on this side. And you can see that what's bright is not necessarily the same at every color. So by changing which wavelength you look at, by changing which color you look at, you're able to find different features in galaxies. Next class, we'll talk about how some of those might relate to star formation, but they can also tell you other things. Certain colors might indicate the presence of dust, and certain colors might indicate the presence of certain gases. So by looking at different colors, you're finding different pieces of the galaxy and you're learning different things about it. The other thing that's important to think about when we talk about colors is that, like I said, a lot of times we talk about a B minus V color, but that corresponds to a specific photometric system. So that has to do, we can only measure a B minus V color if we're using a certain set of photometric bands. So bands are just kind of filters that you put on your telescope. So we block all the light except for the light in this band. So in these set of wavelengths. And I've shown a few on this slide. The ones that get used the most often are the Johnson's cousins, which are up at the top, the UBVRI. I think CTIO uses these. So a lot of publicly available data are going to be in the UBVRI. The others that are getting to be a bit more popular are the SDSS filters down here. So the UGRIZ, they're often called UGRIZ. Similar to the UBVRI, slightly different wavelength set. A lot of times when you're using SDSS bands, instead of doing a B minus V, you use a G minus R for your color. But you can find the color by looking at a difference in any of your magnitude bands, or your photometric bands, sorry. The nice thing about these bands, these are fairly wide. So you're getting, even if you're looking at a faint source, you're looking at a large wavelength range. So you hopefully can still get a good amount of light from that source without having to do extremely large exposures. So I think, sorry, Ethan, yeah.
What are the consequences of the overlap of bands? Like in the top one, like the R and B are almost even overlapping each other, but in like the UGRIZ one, like
so you cut out there at a tad at the end, but I think your main question was about that overlap. That has to do more with how I think filters can be made. So I think that's more a function of how they're made than how they're actually going to be used. So if you can get filters that are more distinct, it's going to in some ways give you maybe more information, but like because you're getting separate fluxes when you look at your magnitude or your colors. But that is more if you take observational astronomy, and Nathaniel will get into more how these filters are made. As someone who just trusts the telescope, I don't know a ton about how they're made or the specifics of why you might choose one or the other. For the most part, what I do is you go to a telescope and they're like, this is the filter wheel we have. And you're like, cool, I want these filters. So you don't get a ton of choice and you just kind of go with what's available. But the main point is that their peaks where emission is 100% essentially are different wavelengths. So that's going to be their effective wavelength. And that's what you're most interested in typically if you're using these filters. Yeah. The other one, I've never seen the Washington or the Hipparcos Tycho filters being used. As someone who doesn't work with Hubble, I haven't used the HST filters often, but if you are working with Hubble data, those will come up. These are also all visual, so these are all optical wavebands. There's also some pretty standard ones that get used in the infrared. So there's the HJ and K band, which are near infrared, and then there's above that there's Spitzer and Herschel both have a set of bands that get to the far infrared. So specifically at 24 microns, 70 microns, 100 microns, and 160. Then there's a few at 250 and 500. But to do infrared astronomy, you really have to be in space as well because our atmosphere is fairly opaque in the infrared. So because of water, which is great for life, but really terrible for astronomy. And then on the other side in the UV, there's kind of two main bands. There's the FUV and the NUV, but otherwise there's not much. So that's kind of a brief overview. If you want to get into the nitty gritty of photometric systems, that's going to be more in observational astronomy. And just as another way to think of bands, I also thought it was kind of interesting to just at least compare it to the human eye. So this is how like we might plot the filter bypass of a human eye, just kind of in the visual light, which is a pretty small region. And then you can also see how that compares to a photometric tube or a photograph, so an old kind of photograph, or a CCD, a bulk CCD that's designed to get all wavelengths of light. So again, this is something that we would talk more about, or Nathaniel will talk more about if you take observational, but just kind of a fun way to think about our eyes are also filtering light. We're just getting all of the optical. Someone's joined. Okay. So the reading for this week was a little open-ended. I asked you to do a little bit of research on one of the telescopes that are often used to do surveys or a survey in terms of things. So I want to try to put you all in breakout groups based on which one you looked into. So if you could in the chat again to me, just send me which of these you did, and I will try to make breakout groups corresponding to those. And then from within your groups, hopefully you guys can come up with like a few facts to share with everyone else about what you learned. It's like we've got, so I will try to do this quickly. Looks like we have some of each, which is cool. So this is going to take me a sec. Sorry. Most of our people have rejoined. Waiting for these two math folks. Here we go. Okay. So let's do it wavelength order, starting with our short wavelength folks at Galax. What do you guys want to share? What should we know about Galax?
Galax is a ultraviolet satellite that looks at galaxies that are pretty old. I think I remember seeing they were about like 10 billion years back. And basically tries to look for star formation rates and just try to see some of the earlier galaxies in ultraviolet.
Oops, sorry. Anything else, Galax folks? So I'll just add that we'll work with some Galax data on Thursday, but Galax is useful because they've pretty much covered any nearby galaxy as well as a bunch of distant ones. So if you need UV light from a galaxy, Galax has both a NUV, near UV, and an FUV filter that all data is available on something called MAST, and you can download, which is cool. So our next wavelength step is our SDSS team. What did you learn?
So just in general, it's like SDSS is like a sky survey, basically building kind of a map of the universe right now. One of their more recent projects, they did a X-ray survey where they found like a ton of new X-ray sources in the disk of our galaxy, but also over like 1 million outside of the galaxy, new sources, which, as the article points out, is about as many that have been detected over the last 60 years. So that was a big breakthrough. And then with that stuff, there was an article about quasars, and it was really interesting talking about how within the span of like a human lifetime, relatively, the quasar winds can change. So it's kind of complicated, but it was really interesting.
Cool, thanks, Grant. Anyone else from the SDSS team want to throw any other knowledge our way?
That was our combined knowledge.
Oh, okay, cool. I'll just add on there again, like that's perfect. SDSS has it's a 3.5 meter telescope in New Mexico, and it's mapped a good fraction of the northern hemisphere sky that it can view in the UGRIS filters. So we will, in your photometry project, you'll be using SDSS data. It's all freely downloadable from the internet, which is awesome. Again, part of this idea was to get just an idea of what data is all out there. But SDSS is a good resource for images of pretty much anything. If you just want huge amounts of data, SDSS has a ton of stuff. So and they've branched out from just doing optical, but initially it was just optical. So okay. Next wavelength step, I believe, is 2MASS.
All right. So 2MASS is the 2 micron all sky survey. And using 2 micron is really great for avoiding dust because the wavelengths don't interact with dust. So we can get like a full sky survey, as the name which is the dust band through the Milky Way galaxy. We can just like see right through it. I'm being told I have internet issues. Can everyone hear me still? Okay, cool. So we're able to get a map of the entire sky, even in that zone of avoidance where it's really difficult to see some like visual light coming through, or smaller like blue light is really hard to see through dust. If a statistical basis for cool objects, and it has also provided a digital sky atlas, a point source catalog, and an extended sky catalog. And then one of the things that we sort of extrapolated that it might longer wavelengths are more affected by gravitational densities than shorter wavelengths are. And that's why like the Earth's shadow is red, because it kind of pulls on longer wavelengths a little harder.
Well, thanks, Ethan. So I think there's a little fading in and out, but I think we got most of it. Just to kind of re-highlight, 2MASS is HJ and K bands, which are about like 1 to 2-ish microns in that range, and then they all are also an all-sky survey. So if you do need near infrared, 2MASS is a great resource for downloading any data. I think you can get 2MASS on MAST as well. It's that same thing that you can get it from Galax, but just another good resource when you are looking for infrared data. 2MASS is a great place to go. So lastly, I think is the Arecibo folks. So that's getting past infrared.
Yeah, so Arecibo is a microwave telescope based out of Puerto Rico. And it was built in the 60s to originally track missiles when they reionized upon atmospheric reentry, and they made a lucky decision to make the telescope move. So it is actually pretty useful for stuff in the 3 centimeter to about 1 meter range. It's a really big, I think it's like 300-meter telescope. So very large, was the largest for a while until someone built something bigger. The FAST array, anyways. So it's very large. It's pretty cool because it was the first place that we got evidence for neutron stars, and then they detected a binary pulsar something or other, which is also really cool. And then it's the source of all the data for the SETI projects. So
Perfect. So I don't have a ton to add there just because I know Arecibo less because I don't work in the millimeter centimeter wavelength range usually, but just as another place where you might turn if you're looking for data as we do this. So no one hit on things, so I'll just really quickly. Things is a H1 survey, so kind of in between, similar to Arecibo, looking at the 21 centimeter line specifically, and then I can't remember what the T is. The H1 is actually H1, and then NGS is Nearby Galaxy Survey. So if you're looking for 21 centimeter information on galaxies, Things is a good place to go for that. Just as a little background to kind of get us thinking about what's out there and where you might go if you want to measure colors. These are good places to start because they will have multiple wavelength bands, images of multiple galaxies that you can then use to get a magnitude and a color. And this is, I think, 2MASS for their redshift survey. Every point there is a different galaxy, and it's color coded by redshift. Cool. Kind of dig into this just a little bit more before we get into our coding project. There are kind of 3 types of bands. There are broad bands, which are what we've been talking about. They're about 300 nanometers wide at least. That's the UGRIS, the SDSS, SDSS is UGRIS, Johnson Cousins. Those are all broadband filters. They're great if you want to get an image of a galaxy without having to wait very long. So they're shorter exposure time because you're open to a wider range of wavelengths. And that's kind of what most telescopes are using. So those are, when we talk about colors, often we're looking at broadband colors. There's intermediate bands, or I guess in this image they're called narrow bands, but these are more 100 nanometers to 300 nanometer wavelengths, and they might grab a couple of spectral features. So I've never seen them used very much. I mostly see broadband or line filters, but it's kind of a step in between. They do exist. I just don't see them used a lot. The more common one are then line filters, which are going to be things specifically focused on one emission line. So pretty often you'll see H alpha filters use it. If you've observed the sun, sometimes they'll use an H alpha filter, which blocks everything except for the 65, 63 angstrom line of hydrogen. And that can also be very useful for galaxies because there's a ton of hydrogen in the universe, so there's a ton of H alpha light. So it's a good way to get information, but it's pretty, these bands are fairly narrow. They're only looking at these one emission lines. So to get a good image of a galaxy, you might have to wait longer so expose for longer because there's less light falling onto your detector because most of it's getting blocked because you're only looking at one line. So we can get magnitudes by just looking at one band. We can get colors by looking at the difference between two bands, and we can use that to make our color magnitude diagrams. So that's what we're going to do now. You guys are going to build your own, just as kind of a little show of how to get there. This will be how you get participation points for today. You'll submit your completed notebook. But on our day 5, under assignments, there's one that says day 5 for galaxy colors, and there's some data that you can download and also a notebook that you can download. Once you've got them downloaded, let me reshare my full screen. Sorry, okay. So if you open Anaconda Navigator, which hopefully folks were able to do, and launch Jupyter Notebook, so you can, whether or not, there's a few people who I think are getting a little stuck on the vote utils step. You should be able to launch Jupyter Notebooks even if you haven't gotten through that. So you click that, stuff will happen, and you'll see a web browser page pop up that is your Jupyter Notebooks, and you can go to wherever you downloaded the file. So for me, my Jupyter Notebooks, I go to my desktop, and then I put them in my nicely named Whitman teaching stuff, and then Galactic classwork. And then I have one for this, and I've got the solutions, and you don't. But you should be able to get to wherever, navigate through your Finder kind of on Jupyter Notebooks, and then open up your notebook, and it should look something like this. So I'm going to put you guys in breakout rooms so you can do this together and kind of help each other, and I'll be popping around. Hopefully you can get to this page. I know it's a little funky, and this will hopefully be easier. The nice thing about these notebooks is that you can both type normal text and have code that can run. So if you hit run on just one of my background things, nothing happens. But if you put run on something that looks like a code, it'll run. And once it says there's a number here, you know that it worked and everything went fine. If there are any errors, they'll pop up there as well. So I've kind of walked through what you need to do in this, and there should be a fair amount of instructions. Just so you all know, if you want to write in code, you just need this box here to say code. If instead you wanted to type some text, answer a question I asked, you could change it to Markdown and then type something, and when you hit run, it'll just show text, but then it'll go back to code once you go from there. So now if I want to say, run that, oh, it didn't like that. That's interesting. Oh yeah, that's because I'm being stupid. Sorry. So if you want to run code versus if you want to just work in text, you can do that here. There's also, you can insert cells if you want more space to do your programming, but anytime you hit run, it should generate a new cell below what you're working on. So if you've done any coding before, this might look a little different from how you normally do it. If you want to run the code in terminal, that's fine as well. I figured this would just be a way for people without Macs to have the same access, and it also is nice because it allows you to type. And if you've used LaTeX, it will accept most LaTeX commands as well, which is cool. So I think that's all. I've made some new rooms that I'm gonna open up, and I want you guys to just work through this and learn a little bit about what color magnitude diagrams look like with galaxies. If you have any questions before you go, you can shout them out now too. Sorry.